Welcome to a lesson with Dr. Powell. Let's take a look at an example of a computation of a Riemann sum. First of all, let's look at the definite integral. Let's look at the definite integral from 0 to 1 of x squared plus 1 dx. Now, we could compute this to be 4/3. Let's see if we actually get that with the Riemann sum. Let's this time use a left-hand sum. And our interval is from 0 to 1, so it has a length of 1. We're taking that 1 and let's subdivide it into n equal pieces. So that means each piece is going to have length 1 divided by n. So the width is going to be 1 over n. With the left-hand rule, what we do is we always choose the x-coordinate on the left part of each subinterval to plug into the function to find the height. So for the first rectangle, we're going to be plugging in x equals 0. The second one, we're going to go 1 width over. And the third one, we're going to go 1 width over. Notice the pattern. 1 over n times 1, 1 over n times 2. 2 is 1 less than 3, 1 is less than 2, 0 is 1 less than 1. Looks like that what we're going to be plugging in is x is equal to 1 over n times quantity k minus 1 to find the height of the kth rectangle. So when we plug it in to find the height of the kth rectangle, we plug it into the function here. So let's plug it in, square plus 1. So that's the height of the kth rectangle. And that's multiplied by the width. Now doing some algebra, square this and square that. In fact, multiply this in, distribute that in, and then distribute this in also to the 1 here. And you end up getting this right here. Now we can split this up into different summations across the subtraction and addition. We can split this up. We're going to group this as 1. In fact, we're going to group these according to powers of k that we see. We see k squared k and here like k to the 0. So we're going to put this in its own sum. Now, when we do that, we're going to factor out of the sum anything that doesn't depend on k because it's going to be the same in each factor. So for instance, this one does not depend on k at all if we put it into its own summation. In fact, that should be a cube right there. Okay. Into its summation. So we could just factor it out. So every single term, I mean, this is like adding up a bunch of these, a bunch of 1 over n cubed plus 1 over n. So we can actually just take all that and factor it out, be left with adding up a bunch of 1s. In fact, we're adding up n 1s. So the sum is just n right here. So we're really looking like we have n times something. Now, when we take a limit of this part, think about this. N times 1 over n is 1. That limits to 1, of course. N over n cubed just limits to 0. So this whole part right here is just limiting to 1 as n goes off to infinity. Now, let's take a look at the other pieces and what's happening. Like for this one, you factor out 1 over n cubed. Now, if you look at the formula for this part right here, what is key and what's most important? What contributes to the leading terms? What contributes to the leading term on the top is 2n cubed. What contributes to the leading term on the bottom is 6. So just imagine just throwing out this formula and just using this, because for limit's sake, that's really all that's important. So in fact, you'll notice something. This looks a lot like n cubed over 3. Hey, that's like the antiderivative of n squared. It does have a lot of correlation there. Okay, so looking at this, we have, so n cubed over 3 is kind of our contribution. And notice, so this whole part, just imagine replacing it with n cubed over 3 times 1 over n cubed. And see, the limit's just going to be 1/3. Over here, you think of something similar. This part right here, what contributes to the leading term in the formula for it is n squared over 2. But then you have an n cubed, n squared over n cubed, then it goes to infinity. That's just 0. This really contributes 0 to the limit. So you have 1/3 plus 1 contribution, which is just 4/3, as we expected. Thanks for watching.